Hey there, Dangar Stu here. Today's video's on measuring voltage drops and a bit of theory about Ohm's law. A voltage drop's what happens when you have resistance in a circuit. So all circuits have resistance in them, but sometimes that resistance is unwanted, and that usually comes in the form of sort of corroded connections and that kind of thing. So this is what we're learning about, is how to find those sections of unwanted corrosion, those bad connections or whatever, and fix them. During this video we'll go through a fair bit of theory about how Ohm's law works and how resistance affects current flow and voltage drops, but I'll always do it sort of in combination with a bit of practical tests using a multimeter and a bit of a made-up circuit. That way you don't get bogged down too much in the blackboard work if that's not your thing. This is the sort of thing I'm talking about, where there's never any shortage of sort of this surface corrosion on boats. So wherever there's boats and wiring, unless it's really done well and really sealed well, you're going to end up with this sort of corrosion, which will definitely add resistance into the circuit and cause a voltage drop. Okay, well let's head back to the workshop and get started. That didn't work. Hang on. We'll start by having a look at a simple electric circuit that just has a battery. Generally, battery voltage is around about, say, 12.6 volts. I've actually tested this little battery and it turned out to be 2.8, so we'll use that for this example. The circuit will have some form of resistance in the circuit, and then it comes back. So essentially you have a voltage, a current flowing along the circuit, and some sort of resistance. And these things all happen in a certain proportion, which is what Ohm's law is. In this case, we can say that voltage equals current times resistance. And this is where we'll decide what this voltage drop is over these different parts of the circuit that have resistance. So when you have a dodgy connection, a bit of corrosion, whatever, it'll have a high resistance, and because of that, the higher the resistance, the bigger the voltage drop will be at that particular junction. In our simple circuit, once the current's flowing, we can start to measure how much voltage is dropping at a particular point. So in this part of the circuit, we've got this one little section that is a high resistance. That could be, say, a particular device on the circuit. It could be this dodgy connection we're trying to track down. But it's only once the circuit is actually flowing with current, it's complete, that we can start measuring the voltage drop across it. So we have this section complete, the device is on. Then we can put the positive lead of our multimeter on one side, near the positive side of the battery, the negative on the other side, and then we'll get a voltage reading with our multimeter set to volts, we'll see that in a second, for how much voltage drops across this device. Now in a circuit like this, essentially all of the voltage will drop on this device because there's no other high resistance sections. Whenever you have a circuit, the entire battery voltage will get used up by the time the circuit's complete. All that shifts is how much gets used up in various points, but you know that that amount, or those amounts, will always total the battery voltage. So if we've got one thing, we're going to get a reading of 12.8, or near as makes no difference, 12.7 maybe, on that device, because this is how much we've got available. It all has to drop by the time we get back to the negative terminal, and we've only got one device, so it's going to use it all. So it gets pretty straightforward. Where this formula comes in handy, not that you need to know the formula as such, but it helps you understand what's going on, is when you have two or more sections of high resistance and you want to figure out how much of the voltage is theoretically going to drop across the separate points. So what I'll do is I'll draw up the diagram of the little circuit I've made here for doing the practical demonstrations. We'll use these formulas to figure out what the theoretical drop should be, so hopefully you can understand how it gets calculated, which will help you understand roughly the types of proportions you can expect. You're not often going to be using these formulas and doing the numbers while you're diagnosing a problem, but by understanding how it works, it will help you in your thinking when you're doing your diagnosis. So we'll draw up the diagram, we'll figure out what the theoretical values are, and then we'll go and do some experiments or some tests with the multimeter and see how close we are to those theoretical numbers. In this circuit that I've made up for these tests, we've got two resistors and a globe. The first resistor is 220 ohms, the second's 1000 ohms or 1 kilo ohm, and the globe actually has a 12 ohm internal resistance in it. So it gives you an idea how the resistance of the device you're running can often be quite low. And what that means is that if you get a bad connection that's giving you a high resistance, then that connection is going to consume by far the sort of lion's share of the voltage, and the device will actually get very little. High resistance devices are a little bit more immune to voltage drop because it all works in proportion. There's no sort of absolutes to this, and the formula is all about figuring out those proportions. So what we'll do is we'll add these up, and we're going to figure out how much current's going to flow around this circuit. And we do that by using a variation of this formula. You're probably aware that formulas can kind of be juggled, and to figure out the current, we do the voltage divided by the resistance. So in this case, with current, as it flows, it doesn't vary at different parts of the circuits the way voltage drop does. Current, once you figure out how much current's flowing in the circuit, it always flows the same amount throughout the entire circuit. So in order to figure out current, we add up all the resistance on the circuit, presuming the wires are zero, divide our voltage, and that'll tell us what we've got. To do this calculation, we just need to substitute this value. So voltage we know is whatever our battery voltage is putting out, 12.8. The resistance is the total resistance in this whole circuit. So we know this is 1232, which is our 220 ohm resistor, our 1000, and then the globe itself. And the current's what we're trying to figure out. Now I found my phone and actually used the calculator because I'm lazy, but essentially it works out at 0.01. The voltage is in volts, the resistance is in ohms, and the current's in amps. So an easier way to think of that is 10 milliamps rather than 0.01 of an amp. So we know this circuit's now running 10 milliamps, and that's what it'll draw. And that kind of thing can be good if, for example, you're putting the electrics in a boat, like a yacht, and you might have quite a lot of equipment in the yacht, and you're looking at figuring out how much current you're going to draw so you know how long your battery's going to last, how much your solar cell and your wind generator is putting back into it. So sometimes doing this kind of energy budget can be pretty important. But in this case, it's more about ultimately knowing, now we know this, let's start using that number in this formula, because now we know the current flowing, and we know the resistance, so we can start to figure out these theoretical voltage drops across these different points. So I'll quickly do the maths for those, and we'll draw them up, and then we'll start doing those measurements with the multimeter. All right, you're doing well there, hanging in with all this chalkboard stuff. We'll have a look now quickly at this complete circuit on the board, and then we'll start doing the practical sort of multimeter. This circuit's got two resistors, the 220 ohm, the 1000 ohm, or 1 kilo ohm, and the globe, which is a 12 ohm resistance through the globe. The formula we saw, which is the voltage drop, is the resistance times the current. So we've got 220 ohms and 0.01 of an amp, or 10 milliamps. So we get 2.2 volts dropping across that first resistor, so a whopping 10 volts dropping across the second one, and the globe's left with 0.12 of a volt, so barely, 0.1 of a volt sort of thing. And that's a 12 volt globe, so it's no surprise that it actually doesn't run with this other resistance in the line, which you'll see. You'll also notice maybe that these don't quite add up to the battery voltage, and that's just due to sort of rounding. This up here, the amperage is 0.01 blah blah blah, if goes to quite a few digits. So it's actually just a rounding error that's caused this not to add up. In reality, the voltage drop across all these resistances in the circuit will always add up to whatever your voltage is the battery supplying. That's kind of one of the key ideas here. All right, so let's start having a look at the circuit itself. So here's the circuit in reality. This is the battery. These are two 6-volt batteries, so I've just got them wired up in here in series to give us our 12 volts. Comes along to this first resistor, which is the 220 ohm resistor. Comes along to the 1000 ohm resistor, to the globe, and then back to the negative terminal of the battery. Just sitting here on a bit of plastic so it doesn't short out given they're bare wires. Now to start measuring these voltages, I've got this multimeter set up where the positive leads into the voltage port, the black lead, negative leads just into the common, and then I'm going to set it to volts here. So the first thing I'll do is just test the actual battery voltage, just by putting the negative lead on the negative terminal battery, positive lead on the positive terminal battery, and we're getting about sort of 12.75, so the voltage has dropped slightly. To test the voltage drop across a particular part of the circuit, and that could be an individual component or a couple of components together, whatever I want. I simply put this positive lead of my multimeter on the side of the circuit closest to the positive terminal of the battery. Then I put my negative terminal from the multimeter on the side of the circuit closest to the negative terminal of the battery. And here you'll see we've got a 2.28. So once again, slightly higher than the theory, mostly due to a bit of a rounding error. But that's the voltage drop across that resistor, pretty much in line with what we calculated using the formula. If I come along here to the 1000 ohm resistor, we'll see we got 10.32, so pretty much the 10 volts we predicted as well. And if we come along to the globe itself, we'll see we're getting 135 millivolts now, so it's dropped right down. So as soon as we measured our voltage across this device, if we were wondering why this globe's not working, as soon as we measured across here, we go, oh, I'm actually getting millivolts. I'm getting almost no voltage dropping here, which means it must be dropping somewhere else, because 12.75 volts is always going to drop on this circuit. If this circuit's connected, the entire battery voltage has to drop along the whole circuit. So if so little of the voltage is dropping over the actual light that I want to run, it's got to be going somewhere else. What I'll show you now is what I think is the most common mistake people make when they're measuring voltage, trying to figure out what's going on if a particular thing like a light like this isn't working. Voltage is measured in parallel, and what that means is that when I put my leads on this particular device, there were two parallel circuits for this length of the circuit. The electricity can flow through the resistor itself, or it can flow through the multimeter. So a very small percentage of the current flows through the multimeter to give us our reading, and that's because the multimeter's got a very high resistance. So the electricity prefers to flow through this resistor than the meter, but we get just enough to actually take the measurement. So that's considered a parallel circuit. If I take a wire off, put my positive probe here towards the positive battery terminal and the negative here towards the negative battery terminal, I'm getting a reading of 12.8. So I'm actually seeing full battery voltage. And that's because I'm now measuring the circuit in series. There isn't two ways for the electricity to flow. It all has to flow through the multimeter. There's no other second path. So by separating the circuit like this, I give myself a false sense that, oh, hang on, 12.8 volts is flowing, so why isn't the light lighting up? And that is true. 12.8 volts doesn't flow. Voltage is sort of a potential difference between the two terminals, and 12.8 volts, or whatever your battery voltage is, will always drop from one end of the circuit to the other end of the circuit. What that's not telling us is how much is getting used up by the various parts of the circuit. So it's only, and the same thing goes if I had this wire coming to the front of the boat, I test this wire, I put the other one to my battery terminal, and I go, look, I'm getting 12.8 volts to here. I'm not. By the time it gets to this light, there's only 0.1 of a volt left to drop. Yes, 12.8 volts is dropping across the entire circuit, that is true, but it doesn't mean it's all left to come here. So don't get this false sense of security that when you come to here, you are actually getting 12.8 volts to this point, even though that's where you're measuring it. So that's something that sort of really just sort of wrap your head around when it comes to voltage drops, is they have to be measured in parallel, and you can measure it across different devices like we did earlier. Now, one thing you do measure in series is current flow, and so that can be a clue. So what I'll do now is I'll just re-rig this multimeter. So I'm going to move my positive lead down here to my little milliamp socket. I'm going to change this to a milliamp scale. So now I'm rigged up for measuring current instead of voltage. And if I come here, and once again I measure in series the same way I did with my voltage, and I'll see now that 10.34 milliamps is flowing through this circuit. So once again that agrees pretty closely, other than the rounding error, with the theoretical calculations we made. Now if you know how much current a circuit's supposed to be drawing, and you think, oh, hang on, this globe actually draws an amp to run, it's only getting 10 milliamps, and that is a way you can detect that there's way too much resistance in the circuit because nowhere near enough much current's flowing. But be careful, because, for example, this circuit is fused at 400 milliamps. If this was working correctly, I would straight away blow the fuse in this multimeter because an amp would be flowing through it, and it would blow the fuse inside the multimeter. So just be careful when you're measuring current, because at that point it's in series, there is no secondary path. The entire current does pass through your tester. Just something to be aware of if you decide to go the route of testing current flow. So hopefully your brain isn't completely fried yet. The next thing I'm going to do is start fixing some of these problems, if you imagine these resistors as problems in the circuit. So I'm going to take out the 1000 ohm or the 1 kilo ohm resistor by just shorting past it, by twisting the wires, and we'll see what effect that has on the amount of voltage that ends up at the globe itself, which is what we're trying to do. So by removing this 1000 ohm resistor, I'm simulating fixing a bad connection, essentially. So obviously, one thing I will say about this formula is you're not going to look at a connection and go, oh, that's a certain shade of green, that must be a 700 ohm resistance problem. You know, you don't. You just know that it's a bad connection and it's giving more resistance than it should. The reason for giving the figures is to show you that it is something you can calculate, but also to show you what a significant effect high resistance has on the voltage that arrives at the lower resistance components. And I think this also gets illustrated by taking these resistors out one at a time. So what I'll do now is I'll take the 1000 out on the board first, we'll recalculate the voltages, and we'll see what difference it has on that light by fixing the major problem with this circuit. So this is the resistor I'm rubbing out. Sorry, this is a dodgy homemade chalkboard that doesn't rub out too well. One thing they taught me when I was at this training class, how to be a trainer, is when you rub a board, always rub it up and down, because if you rub it side to side, it makes your butt wiggle. I don't know. That's a tip for you. So we're going to take that resistor out of the circuit. Now, this will have an effect on the current that flows. Raises, lowers? Anyone? Anyone? Raises. So the lower the resistance, the more current flows. We can't then calculate the voltage drop. Well, we can actually, because it just falls in proportion, so you can do it as a ratio. But to use these formulas, we now have to figure out how much more current flows through this circuit now that 1000 ohm resistor is out. So I'll do that quickly. So to do that, it's pretty simple. We're just taking the 1000 out. So we've now got 12.8 volts divided by 232 ohms, which gives us 0.5. No, I didn't do that in my head. I just looked at it earlier, which is 50 milliamps. So we've jumped from 10 milliamps to 50 milliamps flowing through this circuit. I just double checked that. It's actually 55. So there we go. Now we've got this known new current flow. I can now say I've got 220 ohms divided by 0.55. I don't know if that's in shot, but anyway, I'll let you know the end result. 0.55. And the important thing is what these new voltages now are. Once we've taken this 1000 ohm resistor out, that was sort of the dominant resistance in this circuit by a long shot, what we actually end up with is 12.1 volts dropping over this first resistor and 0.7. So we went from about 0.1 of a volt, so we've jumped to 0.7 of a volt for our globe. Now, bear in mind, when I say first resistor, the order's not important. It's only the ratios, the values that are important. If this globe was before this resistor, the voltage would be exactly the same. It's only because of the ratios they're in. The order they're in doesn't make any difference at all. So this is still now this went from drawing 2 volts, it's jumped 10 volts. This has jumped like half a volt. So I guess the point here, once again, it isn't actually the formulas and the exact numbers. It's showing that you can fix a problem in a boat, in a circuit, still not get a great result because it's still completely living in the shadow of this much higher resistance. So it's really not until this is the highest resistance in the circuit that it will be the one getting the lion's share of the voltage and actually start to operate properly. Okay, so what we'll do now is I'll just show you, we'll go back to the bench again and I'll take that 1000 ohm resistor out of the circuit and we'll have a look at the effect of it. This second one's our 1000 ohm resistor. So all I'm going to do is take these 2 wires and twist them together. With that 1000 ohm resistor out, you'll see we're just starting to get a bit of a glow. So we're getting enough voltage through here to have the globe actually light up, but not enough for it to reach its sort of operational brightness. If I then do the same thing with that 220 ohm resistor, we come up to full brightness. And at that point, if I swap back to the volt socket here, set my multimeter to the volts measurement, we'll see that we're getting 2.4. So we're getting pretty much battery voltage. Obviously there's a bit of resistance being lost in all these connections. A bit of voltage being lost because of the resistance in the other connections. But now those little connections are obviously total much less than 12 ohms. If we're getting the bulk of the battery voltage here, we know that the resistance in these has got to be, less than an ohm almost. And that's what you're shooting for when you're making these circuits, having almost no resistance in the rest of the circuit, so the device can get most of the voltage. All right, so I know that was a lot of theory, and I don't like to do that much theory. I like to try and keep these videos a bit more practical. But I do get a lot of questions about electrical problems in boats, and I do believe the best way to get good at diagnosing those problems is just to understand what's actually happening. I think you might rote learn a few tests you can do in your multimeter, and that's great. You're miles ahead of most people who wouldn't know where to begin. But I do feel that your skills at diagnosing electrical problems will go up immeasurably once you understand just a few simple principles. And really it is just voltage, current or amps, and resistance. And the enemy of all this is resistance, or a low battery. Obviously, the circuit's only going to run as well as the voltage you're actually getting from the battery. So if your battery's good, that's definitely number one place to start. If I was to distill this down to a few sort of principles I'd like you to sort of take away, I guess they'd be that in any circuit, the battery voltage always drops from A to B, from the positive terminal of the battery, whatever you have in the wiring, to the negative terminal of the battery. All the voltage drops across the different parts of the circuit will always add up to the battery voltage. That's sort of the way it is. If you measure voltage drop, make sure you do it in parallel, i.e. you keep the circuit complete, so the current's flowing through that circuit, and then you just take the two probes and you measure on one side, so the positive terminal of the multimeter, on the side of the device or the section you're measuring closest to the positive terminal of the battery, the negative probe of your multimeter on the other side of the device closest to the negative terminal of the battery. And that way you're measuring in parallel. Whenever you take a wire that's not connected, just a loose end of a wire, and if that's connected by some means to the battery, you put your positive probe on that wire, put your negative probe onto your battery, you should see battery voltage. That's the way it is. So don't be tricked into thinking that that's a good circuit just because you're seeing battery voltage. If you measure in series the current flow, you'll see the current's really low in some circumstances because there's high resistance in the line. Okay, so getting 12 volts doesn't mean you're getting a lot of current, and it doesn't mean that by the time you get to that point in the wire, most of that 12 volts hasn't dropped over other sections of high resistance. And then in order to find where that high resistance is, you can reconnect the circuit and just start measuring sections. So if I measured just around that 1000 ohm resistor originally, I would have seen it was 10 volts. If I measured just around the 220, I would have seen it was 2.2 volts. And if I measured across both of them, I would have seen it was 12.2 volts. So you can see how much voltage is dropping on any part of the circuit. And that'll help you start to narrow down where this section of high resistance is. And then once you've found it, it's really about cleaning it up. So let's just have a quick look at that now as another sort of practical thing, and then we'll wrap up. This is a pretty common, I don't know if it's going to focus, pretty common sort of corrosion you get on copper in boats. So if I take these sort of corroded wires, twist them together a bit, go to a resistance setting on my multimeter. So you can see here, what am I getting? It's sort of varying, but that wire connection there is actually showing me 250 kilo ohms. You saw what a huge effect even 1000 ohms or 1 kilo ohm had on a circuit. So it's not hard to see how that is 150 times worse, literally, than the resistor we had in the circuit before. So almost no voltage is going to make it to the end. All the voltage is going to drop trying to pass this resistance. So what we do about it, obviously, is make some nice connections. Now in this case, you could cut this wire back. You can even see that green stuff coming off. Sometimes the corrosions actually travel along the casing a fair bit. So another thing you can do, this I've had forever and a day, it's actually even leaking, which is bad, is an old tub of hydrochloric acid. Be careful when you open it, these fumes are really nasty to breathe. But if I take this connection, dip it in there for a little while, maybe give it a swish, it comes out looking much better. So a bit of acid like that can be a really good way to clean up an old corroded wire. So if I do that to both ends, so once again, pretty green. Give it a bit of a dip. It doesn't take that long to come up looking pretty much like copper again. Then I'll clean these up and we'll join them and we'll see what sort of resistance we start getting now. Traditionally, I've been a huge fan of getting the soldering iron out, soldering up connectors, putting a bit of heat shrink on them. But I must admit, more and more I'm actually liking these style connectors. Sorry, I keep forgetting where this lens is on this. It's actually using my phone because my camera died. But I've ordered a new one, so it should be better soon. They have some really low temperature solder in the center here, a bit of a sort of an adhesive here that grips onto the wires, and then the rest of it's sort of a heat shrink. So what you'd do is slip this connector over. Then I'd get these. I tend to sort of try and mesh the wires a little bit, like separate them. And then sort of mesh them a little bit and twist them. Like that. And then push this connector back over so that the center, the solder part here, is right at the center of the actual connection. And I'll heat this up and I'll show you what happens. So now I've got this connector sitting on the wires with the solder section right in the middle. I'm going to heat it up with a heat gun, which is just a hairdryer for the workshop. They're hotter though, they're much hotter. They'll melt things, whereas hairdryers tend to be relatively cool. I've got this set to its highest temperature. And I'll come in here, hopefully I can focus close enough so you can see what happens. So once I start heating it, the first thing that happens is the heat shrink closes up, and eventually you'll see that center solder is also melted. So I don't think this can focus that close, but there, that center strip is no longer a band, it's now melted through the wires themselves. How successful that solder is depends on how clean the wires are. Solder won't stick to corroded wires, so that's why that acid dip at the start is really important, or cutting back to clean wire. Back at the bench now, I've got this multimeter in the resistance testing mode still. And if I look at it now, we're getting 0.1 of an ohm. So the difference between a good soldered, clean soldered connection and twisted corroded wires was 250,000 compared to 0.1. So it's a massive difference. I'm not saying that's a startling result, or a surprising result, should I say, but when you look at how much of a voltage drop happened across 220 ohms, you can understand why these bad connections rob the devices on your boat, your bilge pumps, your nav lights, of so much voltage and so much current. So that's why doing these connections properly is important, and using these techniques to find the bad connectors can help you get to the point of having solid, reliable electrics. That about wraps it up for today. Thanks for watching. I hope it wasn't all a bit too theoretical, but I do believe understanding what's going on with electricity really helps you diagnose problems more than just rote learning a couple of techniques does. So I hope this information sort of serves you well through the future if you are the type of person who likes to diagnose their own electrical problems on a boat. Because let's be honest, a lot of it's mechanical, but a huge amount of it's electrical. You know, that people will say, oh, I turn my key, I'm not getting any current to the forward control, something I spoke to someone about recently. Which brings me down to the point actually. When I spoke to them, they said, oh, maybe I have to replace the loom because one of the wires was broken. And this is actually a problem I had in my own boat. Don't be afraid to just start doing your own wiring. In this case, it was the one wire that carries the power that was broken, and I had the same problem in my boat. So just run a separate power lead, just a single core wire. You're going to spend $10 on wire instead of buying another $200 loom. So I think once you get your confidence up with this, you realise that, no, I don't need to go and buy a many $100 Yamaha loom. I can actually just run a separate power lead from the motor, the same point that loom wire picked up, run to the front, problem solved. You've now just sort of decommissioned that one wire inside the loom and you're all good to go. So I think getting your confidence up with electrical problems can save you a lot of time in labour paying someone to diagnose them, but also give you the confidence to fix the problem maybe in a way that a workshop wouldn't, and save yourself even more money again. All right, well, thanks again. If you enjoyed this video, please rate, comment and subscribe, and I'll catch you next time. See ya.